Today's learning goal is to solve two-dimensional constant velocity problems. Solve two-dimensional constant velocity problems. So we have a problem here that we should try to solve. It says a scientist in Antarctica is trying to find an outhouse to go to the bathroom during a blizzard. She walks towards the outhouse 6 meters away in the y direction at a pace of 1.5 meters per second in the y direction. A crosswind causes her to drift in the x direction at 0.5 meters per second. Find her displacement by the time that she should have expected to find the bathroom door. Really pretty similar to the problems that we've seen so far when we've been dealing with motion in one dimension, but now we have another direction to worry about. So in addition to motion in the x direction, we also have some motion in the y direction. So the first step should be to draw a diagram of the situation so that we can better understand what is happening. So we're going to take it one sentence at a time. So we've got a scientist in Antarctica trying to find an outhouse to go to the bathroom during a blizzard. So the idea is she's outside, there's a snowstorm out, and she can't see. So she thinks she's walking towards the bathroom, but she's getting pushed by the wind. Let's go ahead and draw. Here's my x direction and my y direction. So y and x. And let's go ahead and draw the outhouse. So here's the toilet. And then the scientist, let's draw a top view of the scientist. So here's the head of the scientist. Here are the shoulders of the scientist, and then we'll put some little arms outstretched forward like they're trying to find their way around. Oh my gosh, this looks like this person could be Popeye. There's some big forearms. Okay, but the idea is we're looking from the top and they've got their hands stretched out in front of them because they can't really see where they're going. And the outhouse is 6 meters away in the y direction from where she starts walking. So this distance here is 6 meters. Okay, so notice the 6 meters is in the y direction, and this is how far our scientist is going to be moving in the y direction. So let's call this the change in the y position, delta y. Okay, let's keep reading. So it says now that a crosswind causes her, oh wait, 1 second, oh, I'm going too fast. Okay, so it says towards the outhouse 6 meters away in the y direction at a pace of 1.5 meters per second in the y direction. Okay, so I have to interpret, what does this mean? A pace of 1.5 meters per second in the y direction. Meters per second are the units of speed. So she's moving at a speed of 1.5 meters per second in the y direction. Let me add that to my diagram. So there's some motion happening in this direction, and speed, we use the letter v for velocity, and we should be specific because this is her speed in the y direction. So let's put a little y next to our v to show that this is the speed in the y direction, is 1.5 meters per second. Okay. And then it says a crosswind causes her to drift in the x direction at 0.5 meters per second. Again, meters per second is the unit of speed. So they're giving us the speed with which the scientist is moving in the x direction. So let's add that to our diagram. The x direction is this direction. So we're going to add a velocity vector in the x direction. So we're going to call this the velocity in x, vx, is equal to 0.5 meters per second, right? This is what it said in the problem. A crosswind causes her to drift in the x direction at 0.5 meters per second. Okay, so there's like a wind. Let's draw like a little, some like curly air, like sort of windy, it's windy conditions. I'm gonna show my, like the wind blowing across. That's causing her to drift this way at a constant speed. Okay, and then we wanna know, find her displacement by the time that she should have expected to arrive at the bathroom door. So she's walking forward towards the bathroom, but at the same time she's being blown by this very cold wind towards the side, so her overall motion is going to be kind of like diagonal like this. Even though the scientist doesn't know that she's drifting, she's going to be moving towards the side kind of in a diagonal way, and she's going to miss the bathroom. She'll never find the bathroom. Okay, so we want to know what is her displacement by the time that she should have expected to find the bathroom door. Okay, so notice this is important. The displacement of the scientist is going to be a vector that looks something, I got cut off, a vector that looks something like this, right? This is what we're ultimately looking for, is this vector here. Let's call it lowercase d for the displacement vector. and I'm going to draw it in blue so that it like stands out. So this is the thing that ultimately we're going to try to find. But we need to like find some things in between. This is going to be like the final answer. This is a multi-step problem. Okay, so in order to define this displacement vector, we know the y component of that displacement vector. We need to also find out the x component. So the x component of the displacement vector delta x, this is something that we're going to need to find out eventually. And we also, let's take a look at the problem. It says, find her displacement by the time she should have expected to find the bathroom door. Okay, so one of the things that we're going to also have to find out is how much time does it take for her to move from her initial position to the bathroom. So this is, there's a question of, there's a question of time. What is the time, the change in time, for her to find the bathroom? Okay, so let's begin. We have our diagram. Okay, so these two-dimensional motion problems, the strategy here is that we should treat the motion in the y direction and the motion in the x direction separately. That way, instead of having one two-dimensional motion problem that's maybe too complicated for us to solve, we can break that down into two one-dimensional motion problems. That is something that we're comfortable with. Okay, so I'm going to begin by looking at my y direction, the motion in the y direction, because I know more information about what's happening in the y direction. I have a y velocity, I have a displacement in the y direction, and I want to know what is the time for her to move from the starting point to the y position of the toilet. Okay, so question number 1, how long does it take for the scientist to reach, or rather to move 6 meters in the y direction? Okay, so this is going to be the first question that I'm going to have to answer in order to answer the overall problem. So how long does it take for the scientist to move 6 meters in the y direction? Okay, let me write down all the information that I have about the scientist's motion in the y direction. I know that she's moving with a speed in the y direction of 1.5 meters per second. I also know that the displacement in the y direction is 6 meters. Whoops. And I want to know how much time does it take to complete that displacement of 6 meters. So this is what I want to know. This is my question mark. Okay, so I've got velocity, I've got displacement, and I want to know time. Well, if you remember from earlier in the year, the velocity can be written as displacement divided by time, the change in position over the change in time. So my y velocity is going to be my displacement in the y direction divided by the change in the time. Let me substitute in value, so 1.5 is my velocity. The displacement is 6 meters, and the change in the time, I don't know, so I'm going to leave it as delta t, and I'll solve for that. Okay, so to solve for delta t, I should first multiply both sides of the equation by delta t, because I need to try to get it out of the denominator. Let me move this up here. So multiplying both sides of the equation by delta t, I'm going to have 1.5 times delta t equals 6. And then I'm trying to solve for delta t, so I'm going to divide both sides of the equation by 1.5 to try to get delta t by itself. And delta t is going to be, let's see, 6 divided by 1.5. 6 divided by 1.5 is 4. And the units of time are seconds. Okay, so now moving on to the second part of the problem. Now that I know the change in the time, I'm going to try to find out, okay, how far does the scientist move in the x direction during that time? How far does the scientist move in the x direction during those 4 seconds. So let's see. Again, I'm going to write down the given information that I have, everything I know about her motion in the x direction. I know that the velocity in the x direction is 0.5 meters per second. Now I know the time that she's going to be moving in the x direction. Right, I didn't know that at the beginning, but I know it now. And I'm looking for how far does the scientist move in the x direction. That's the displacement in the x direction, delta x. This is my question mark. So once again, I've got velocity, change in time. I'm looking for a displacement, delta x. So this is going to be, I'm going to have to use the velocity equation. Velocity in x is displacement in x over time. Substitute in the information that we were given. So 0.5 is the velocity in the x direction. 4 is the time, 4 seconds. And then change in position, I don't know. That's what I'm looking for, so I'm going to leave it as delta x. So to solve for delta x, I should multiply both sides by 4 to get the 4 over to the other side. Right now it's dividing, so I'm going to multiply to undo that division. And so we've got that delta x is equal to 4 times 0.5, and 4 times 0.5 is equal to 2 meters. Okay, so let's see. Now I know that the displacement of the scientist looks something like this. So remember, we were being asked at the beginning to find the displacement of the scientist, and we were given that the scientist moves 6 meters in the y direction, and we just found out that while she moves 6 meters in the y direction, she also moves 2 meters in the x direction. Okay, so let's write down the displacement vector. The displacement vector is going to be, well, 2 meters in the x direction. That's the x component of the displacement, plus 6 meters in the y direction. 6 meters in the y direction, that's the y component of the displacement. And this is our final answer. That the displacement of the scientist is going to be 2 meters in the x direction and 6 meters in the y direction by the time that she should have expected to find the bathroom door. She missed it. Okay, great job everybody. So remember, let's recap really quick. We had this kind of very complicated sort of a problem at the beginning. So we split the problem up into 2 problems. We found the time that it took to move in the y direction, and then we used that time to find out how far we had to move in the x direction to get our final answer of the displacement is 2 meters in the x and 6 meters in the y. All right, great job.